Our 13th lecture is going to be on homotopy of spaces. Previously, we've talked about homotopy of paths. So previously, we discussed path homotopy. This is when you can continuously deform one type of path into another type of path. But now we're going to discuss space homotopy. This is when you can continuously deform one type of space into another type of space. The two spaces do not actually have to be homeomorphic. And this is going to be our last lecture about the general properties of the fundamental group before we start doing calculations and about how you find the fundamental group and things like that. This would be very helpful because it is very convenient to quickly calculate the fundamental group of some kind of space. Often, if I give you a topological space, if you can identify it as being homeomorphic to a space that you are familiar with, then you can immediately get the calculation for the fundamental group. But sometimes you will have spaces that are not going to be homeomorphic to anything that you're familiar with. However, they are going to be homotopic to something that is more familiar. You'll be able to continuously deform that space into something that you already know, and then you'll be able to immediately know what the fundamental group is without doing much work. So this is why we want to discuss this. So we're going to talk about homotopy of spaces. So I'd like to begin by reminding what it means to be a homotopy of paths. So this is just a quick reminder. So this is review. Let F and G be paths in X from P to Q. So paths. So that just means you have a function from the unit interval. We think of the unit interval as representing time. We think of this as the t variable. So as the time goes from 0 to 1, we're flowing from P to Q with the requirement that f of 0 is P and f of 1 is Q. This is, of course, a continuous mapping. And then G does something similar. So G of 0 is P and G of 1 is Q. That's what it means to have two paths from P to Q. And we say, F is homotopic to G, path homotopic. I think Moncrief puts a little p at the bottom to indicate this is path homotopic, but I'm just going to be lazy and I'll use suppressive notation, and then we'll just understand from context what we're referring to. So path homotopic would mean that there's a homotopy, there is a continuous interpolation, so let's call it H, from I times I into X. So you think of the first one as representing time, you think of the second one as being interpolation, and the following, this is a continuous map, of course, and it satisfies the property that at time 0, for any value of S, it's always equal to P. At time 1 and value S, it's always equal to Q. But when S is 0, you get f of t, and when S is 1, you get g of t. And the picture, of course, here is this is P, this is Q, this is F, this is G, and then the homotopy is sort of producing intermediate paths in between them, and it interpolates one to the other. And as you can see, they always start at P and they always end in Q. So that's what we mean by path homotopic. So this path condition is satisfied, that P and Q, they sort of stay fixed throughout this deformation process. So now we're going to slightly change things. So this is going to be slightly different. Now, if you look at a path is a continuous function from one space to another space. So let's now introduce this new definition. So definition. So let f and g be paths. Now a path is a function. So instead of calling it I and x, let's call it be continuous functions from one space into another space. You see, this is where the difference occurs. That when you're working with paths, it's a continuous function specifically from an interval into some space. But now, more generally, when we talk about homotopic functions, we're going to define what it means to be homotopic functions. So f and g are, this is one function, this is the other function. And now there's none of this stuff with the base point, time 0, time 1. So that kind of all goes away. So f and g be continuous. This picture will also go away because these are no longer paths. These are just two continuous functions. And we say that f and g are homotopic. We just say homotopic. Homotopic as continuous maps. If there is a homotopy, now this is where the difference occurs. Previously, we had an I over here, and we had the I. So this was like the interpolation from f to g. But now we're mapping x to y. So here we're going to have x. Here we're going to have y. And we're going to say that f and g are homotopic. So this is no longer path homotopic. This is just homotopic as continuous functions. If there is a homotopy, so previously it was a path homotopy, but this is just a homotopy between continuous functions. So as before, you think of this as being s. You think of this as being the interpolation parameter. And this time you remove this condition. This will make no sense. h0 of s is equal 0. I mean, this is no longer an interval. So you remove this one, and rather this is the condition, that ht of 0 gives you the first function. And when s is equal to 1, it gives you the other function. And then when s moves between 0 and 1, you're continuously changing one function into another function. That is the idea of what is known as a homotopy between two continuous functions. So as you can see, it's very similar, but it's a little bit different. And now I want to tell you what homotopic spaces are. So I think I just want to put down some definitions, and then we'll look at a number of examples. So let's take this down, and let's say what it means. So just maybe a reminder. X and y are homeomorphic, or you can also say isomorphic as topological spaces. So you say that x and y are homeomorphic if and only if you can find continuous functions from x to y and a continuous function from y to x. This is a little bit different from the way we've defined it before, because previously we said that there's a continuous bijection whose inverse is also continuous. But then I'm just calling g to be the inverse, and it's continuous. So there's continuous functions, right? These are, of course, continuous functions. So when we're working in the category of topological spaces, so just to use that vocabulary again, in the category of topological spaces, it is always assumed that the maps, or what you call the morphisms, these are the allowable maps within the category, are going to be continuous functions. So sometimes we get sloppy, we just say function or map, but it will always mean continuous unless otherwise noted. So you can find continuous maps so that f composed g, that would be the identity on y, and g composed f, that would be the identity function on x. Okay, so that is the definition of what it means to be homeomorphic as topological spaces. So now we're going to define something that is very similar, but it's more general. It allows you to know if two spaces have the same fundamental group, even though the spaces could be different topologically. And this is the new definition. This is the new definition. So x and y are homeomorphic. So let's say homotopic spaces. I think Moncrief says that they have the same homotopy type. I think that's the way he says it, but I'll just say homotopic spaces. So if and only if you can find a a continuous map from x to y and y to x, so that when you do these compositions, you do not necessarily get the identity, but you get something that is homeomorphic to the identity. So that would mean that this composition is something that be continuously changed into the identity. And then F and G are called homotopic inverses. So they're sort of like inverse functions, but not quite, because they're not equal to the identity. There's a homeomorphism. I'm sorry, there's a homotopy to the identity. So if you want to just write it out more carefully, maybe just for practice purposes, let's just say what this means. So what does this mean? So this is just to reinforce. Reinforce. I'm not sure how to spell the word reinforce. So let's misspell it, reinforce. So to reinforce the definition. So this would mean that there is a continuous map, let's call it H. This is what we call the homotopy. So the identity. So the identity is a mapping from x to x. So there's an x times I into x. So when time, let's say, is equal to 0, I know I previously called it s, but if you want, you can think of this as time, because there is no path over here, so there's not going to be confusion. Or you can think of it as s, does not really matter. So this would mean that h of x comma 0 is equal to x. That's the identity mapping. You see, that's the identity mapping where x is mapped to x. So you have this, and then when time is equal to 1, that would be equal to this. So that would be equal to g of f of x. So we're saying that there's a continuous interpolation that takes you, so it satisfies these properties that in the beginning it takes you from the identity and it gradually changes it to that function. So that's the meaning of this, that you can achieve something like this. And then something very similar happens with this one. So this is the definition of homotopic spaces. And now I want to show you some examples. I guess I should say one more thing, why we care about this. So F and G are called homotopic inverses. I think Moncrief calls this, I think you might also call this homotopic equivalences. And maybe there's other words you can use. And this is the theorem that we want to get to. This is like the main theorem of this lecture. In fact, this is really the one thing we're going to prove after we do our examples. And that is, if F is a continuous map between two spaces, and f of p is equal to q, let's say it maps some point to some other point q, and f is a homotopic equivalence between x and y, between these two spaces. So then when you have a continuous map, the continuous map induces a homomorphism on fundamental groups. So you're going to have a homomorphism on your fundamental groups, and this homomorphism on fundamental groups is an isomorphism. So this is going to be an isomorphism. And this is why we care about it. You can easily imagine situations where maybe this is something which is like some kind of strange space that you're not familiar with, and this is something that you're comfortable with, something that you've seen many times. And if there's some kind of homotopy between the two, homotopic equivalence between the two, then you know that whatever that homotopic equivalence is, it will give you an isomorphism between the two spaces. So you can immediately know that the fundamental groups will be the same. So then you're not going to be confused about what the fundamental group is in this space. You can just use the knowledge of this fundamental group. So this is the way this gets used. You can certainly imagine the benefit of something like this, because you're not just confined to homeomorphic spaces. It gives you a larger class of spaces to use to help you find the fundamental group. So now let's do some examples. Okay, so the intuition you want to have, so this is the intuition that you want. The point of these examples is to sort of help you with some of the intuition, so you have some picture in mind about what you're doing. That you can argue that's more difficult than the actual definitions. The definitions are one thing, but do you really get it? And when you really get it, that's when you have the intuition for what you do. Well, actually, I should say, when you really get it, it's when you can convert your intuition into formal proof. So that's when you really get it. But you need both. And you cannot just do math using formal definitions. You're not going to get very far. And you cannot do math only doing intuition, because then it's everything you prove is very suspicious. And a lot of the times you're going to make mistakes, because sometimes things are bizarre and it's not what your intuition says. So you really need both. Your intuition is supposed to guide you in what you do. So the intuition that you want to have is X and Y are, okay, if two loops are homotopic, and it means we can continuously deform one loop into another loop. That's what it means for loops to be homotopic. So that's what we've talked about before. And if two spaces are homotopic, which is what we're talking about now we're talking about topological spaces being homotopic, then it means we can form one space into another space continuously. Now, you might feel that how is this different? So this is like the immediate question you want to have in mind. How is this different from a homeomorphism, you might ask? Homeomorphism. How is that different? Is it not the case that when you have a homeomorphism, you're sort of twisting and bending the space into another one? But here, you're actually allowed to change the topology. So let's perhaps look at an example that will help clarify this. So I'm going to give you an example, and this is probably the most extreme example, but we should know this. This is an example. So this is useful to know, that if C is some subset of Rn, and it is convex, and let's say you pick some point in your convex set, so then C is homotopic to that single point. It's homotopic to a single point. Now, when we draw a picture, hopefully this will clarify what's going on. So take your favorite convex set. Let's say this triangle. Well, we'll keep it simple. So this triangle is a convex set. So of course, all of that region included, but I do not want to draw those lines. It will maybe make the picture a little bit confusing. And then you pick a point somewhere inside. It does not have to be in the middle. It does not matter where it is. And then you can imagine that you took this triangle and you shrunk it a little bit, right? You've continuously shrunk the triangle. And then you took that triangle and you shrunk it a little bit more, and then you shrunk it a little bit more, and you shrunk it a little bit more. And as you keep on shrinking it, in this continuous process, it keeps on shrinking and shrinking and shrinking until it shrinks down to a single point. You see, it's just like when we say, so it's exactly what we say, that a path is homotopic to the constant path it means that we can sort of take that path, undo it, and then keep on shrinking it and shrinking it until a single point. So there we are shrinking a path, but here we're shrinking an entire space. So it's very similar to what you're doing with paths, but now you're working with actual spaces. So you're shrinking your space down to a point. And so the convex set is homotopic to P. And the picture here, you would use the straight line homotopy. So it's important that you have a convex set, because for any point, so you basically, for any point in your space, you always stay within your space, no matter where you are, sort of always staying. If you just draw various lines, you can kind of move along lines, and you're always staying within your space. This is why being convex is very helpful here. So how do you prove it? So to prove this rigorously, so how does one show this rigorously? So to justify this rigorously, we need two maps, of course, continuous maps. One of them is going to map our convex set into this point, and then we're going to have another continuous map that's going to map the point into the convex set. Okay, so how are they going to be defined? And these are going to be defined as follows. So f of x, so if x is a point in the convex set, well, this is a single point space. So that means everything in C has to be mapped to P. There's like no other, I mean, there's no other choice. It has to be mapped to P. And this one is kind of the same idea. This is a single point, right? So G is only determined by what it does to a single point. So where do you map the point? It has to be in C. Well, for convenience, you can really map it anywhere, but for convenience, let's just map it to P again. So this is sort of like the identity. So we need two maps, and this is the way we're going to define these two maps. And we are required to show, so this is the definition of homotopy equivalence. If we want to say that this space and this space are homotopy equivalent, we have to show that if we do F compose G, that's not necessarily, so it could be the identity, but it's homotopic to the identity. So this is going to be, so this one goes first, so this has to be homotopic to the identity on the single point space. And if you do it the other way around, that has to be homotopic to the identity map on the convex space. So we have to verify these. Now, if they happen to already be identities, then the spaces are actually homeomorphic. And then if they're homeomorphic, then then they certainly have the same homotopy type. But more generally, they might not be homeomorphic. And clearly, I mean, the convex set is not homeomorphic to a single point, unless it happens to be a single point itself. For the simple reason, because this contains an infinite number of points that contains just one point. There's no bijection between them. So you cannot even find a bijection, any bijection between them. So this is the condition we have to check. We have to check if those two compositions are homotopic to the identities. So let's look at the easy one. Let's look at this one. G goes first. So if G goes first, G of P is P, and then F of P, well, F of anything is P. So this is actually is the identity. So we wrote homotopic to the identity, but this one actually is the identity, which is not a surprise because you just have a single point. So that actually is the identity. So there's nothing to do with this one. So this one has already been done. That's all fine. So this is the one that we have to work with. So let's actually calculate what this is. So let's just see what this is doing. So if we do G of F of X, what is that? So F, that's a point in C. F maps every point to P, and then G of P is equal to P. So that's equal to P. And the identity on C at X is equal to X. Okay, so these are the two functions. So we need a homotopy. So we need to construct a homotopy between these two functions. So between G composed F and the identity on C. And by the way, both of these functions are functions from C to C. Right? This one is a function from F goes from C to the point, G takes you from the point to C. So both of these are functions from C to C. So this has to be a homotopy between these two spaces. So here's how we construct it. So we will use the straight line homotopy, which we used before. And this is only possible because you have a convex space. So this is the straight line homotopy. So H is going to be our homotopy mapping. So here's the way it's going: is C cross I into C, right? You're going from C to C, and then you introduce this interpolation parameter, call it S, or call it T, does not really matter what you call it. And it's supposed to have the requirement so that so that the condition that H of x comma 0 gives you the identity, and H of x comma 1 gives you the, you see you have two functions here. You have the identity and you have P. These are the two functions. Which one is first and which one is second does not really matter, because if A is homotopic to B, then B is homotopic to A. It's just like with paths. It's kind of like an equivalence relation. It does not matter in what order you do it. So let's suppose at S is equal to 0, you want to have the identity, and when you set S is equal to 1, you get the other mapping, which is the constant mapping, and it gives you P. So you want to have some kind of continuous interpolation between these two. And the way this is, you define H of x comma S in the following way. So this would be 1 minus Sx plus Sp. Okay, and just to reinforce something, this is a scalar, because that's a number between 0 and 1. That's a scalar. That's a number between 0 and 1. This is a vector. This is something in Rn, because C is something sitting in Rn. And P, this is also a vector, because that's a point in C. So it's a subset of Rn. It's an element of Rn. And you're just taking this vector, you're rescaling it, and you're adding it another rescale vector. And this is a line segment between those 2 points. And this is very important. Whatever this is, the target, you see, whatever this is, it lands back in C. So you've constructed a valid homotopy that takes you from here to there. You cannot just write Rn. That's not allowed. It actually has to go back into C. That's the requirement of the definition. And this is only possible because the C is convex. So this is a safe way to do it. You know that in the end it's going to work out. And the picture of the straight line homotopy is quite simple, that your convex set, however it might look like, you have your point P, and the way this works is, this is like your fixed point that you're sort of collapsing everything down to. And if you have any other point X in your convex set, what you're doing is you're connecting it by a straight line. That's why we call it a straight line homotopy. And then if you make S go from 0 to 1, you start on one of them, you end up on the other one, and then you're continuously moving from one to the other. So you're continuously deforming yourself from this function to that function. So you have constructed a homotopy between these two. And so it means that in a convex space, it's homotopic to just a single point, okay? And the picture makes sense why it's just a single point, because the whole thing can be continuously shrunk down to a single point. Let's actually make a definition, because sometimes this comes up. So let's make this definition. Definition. We say X is a contractible space if and only if X is homotopic to a single point. That's what we call a contractible space. Now, to avoid confusion, I want to discuss the difference between a simply connected space versus a contractible space. So And we'll do it like this. So we'll give the rigorous definition, and then we'll give the the intuitive definition. So they'll both be helpful. So what's the rigorous definition? So the rigorous definition is that X is simply connected if and only if it is path connected, and the fundamental group of X. I'm not going to put the point here. I don't want to emphasize it. The fundamental group anywhere is trivial. So it's just the homotopy class at any point, based at any point, consists of just a single class. And the rigorous definition of a contractible space is X is contractible if and only if X is homotopic. So not homeomorphic. I'm not sure what symbol to use for homotopic, so I'll just write it like that. Homotopic to just a single point. So it's a different definition. Now, if a space is contractible, it has to be simply connected. The reason for this is because that's the main theorem that we mentioned. The fundamental group of X would then be the fundamental group of a single point, and the fundamental group of a single point would be trivial. So if a space is contractible, the fundamental group will automatically be trivial. You might be wondering if it's contractible, is it path connected? Yes, it will also be path. You can check that. That will necessarily be implied. So yeah, it's homotopic to a single point. And now what's the intuitive? So which one implies which one? So clearly a contractible space implies that you have a simply connected space, right? That's clearly the case because of this. But the other way around is not true. But before I do that for you, I want to give you the intuitive definition. And then after you get the intuition, maybe you'll be able to think of your own example. So this is the intuitive definition. X is simply connected if and only if all loops in X can be shrunk down to a point. And here the intuitive definition would be that X is contractible if and only if the entire space, not just loops, you see, that's why it's saying more, that the entire space can be shrunk down to a point. So that's the difference. And now you can see why this makes sense. If the entire space can be shrunk to a point, then loops, which are part of the space, that's like a smaller subspace, can also be shrunk down to a point. Now, what's the example that shows you something that is simply connected but not contractible? So, an example of something that is simply connected but not contractible. And you should be able to find this example. You can even pause the video and take a few minutes to think about this. So here's the example. So the example is S2. This is the two-dimensional sphere. Two-dimensional sphere. This is not contractible. So let's look at the picture for why that's not the case. So if you have a loop, so it's simply connected because if you take, let's say, the North Pole and you have a loop over here that goes around the sphere, it's clear that you have space inside that allows you to keep on shrinking it down to a point, and then the loop disappears down to a point. But the entire space itself cannot be shrunk down to a point. And some of you might be asking this question. Some of you might be asking, well, can you not draw a smaller sphere, and then you draw a smaller sphere, and you keep on drawing a smaller and smaller and smaller sphere, and as you keep on doing it, the sphere disappears and it turns into a point? And that's a great question. Now, to answer your question, why that is cheating, so basically what you're doing is you're cheating, is let's go back to the punctured plane. Okay, this is our punctured plane. We have a hole in the middle, and I have a loop that goes around it. And I'm gonna show you why this loop contracts down, can be collapsed down to a point. So I can say, take this loop and lift it up. So lift it up, flip it over. So flip it over on the other side, right? So you lift it off the paper, you flip it off on the other side, and then you can take it and you shrink it down to a point. So that would be cheating. So this is cheating. You're not allowed to do that. And the reason why this is cheating is because when you shrink a loop down to a point, you have to stay within your space, right? You're not allowed to leave your space. The moment you start lifting the loop off the paper, you're leaving your space. So that's why we're saying it's cheating. So the same thing is happening with the sphere, that the moment you start drawing a smaller sphere sitting inside it, and you keep on doing it until you get to the very center, the center of the sphere, that's not part of the sphere, and the smaller sphere is not part of the sphere. Now, if the sphere, however, was a solid ball, right? If you had a solid ball, well, we can see it's convex, but if you had a solid ball, then absolutely you can do it, because then you're moving within your space. You're not leaving your space. You're not going into a different space. That's kind of like the intuition for that. So this is an example. So this is a nice example of something that is simply connected but not contractible. Now here's actually the funny, the very funny part. You might find this very funny. We will be unable to prove this. We will be unable to prove that the two-dimensional sphere is not contractible. The reason, I mean, you might find it funny, but the reason for this is because it means that the fundamental group of the sphere at any point, let's not really worry about the point, would be the fundamental group of a point. And the fundamental group of a point is trivial. So, and that's the difficulty, that a contractible space has a trivial fundamental group, and the sphere, the two-dimensional sphere, has a trivial fundamental group. So if you're only using the fundamental group, it is not strong enough to show you why it's not contractible. Now, what you could do is you can use these things called higher homotopy groups, and you can talk about like the two homotopy group of S2, but we're not, like in topology part 2, you're not really going to talk about that, because homotopy groups of higher order are not very easy to work with. Instead, you use these things called homology groups, which will give an insight of what they mean later on. But you have a homology group H1, H2, H3. They're kind of similar to the fundamental groups, but they're just defined a little bit differently in an easier way. They're easier to work with. And then you'll be able to show that this is not trivial. And then from there, you'll be able to conclude that therefore the fundamental group of the two-sphere is not contractible, because if it was contractible, it would have to be a single point. So that's what we're not going to do it this semester, but if there's a continuation course and you talk about homology, then you'll have the tool available to show that rigorously. So that's actually kind of funny that it sounds fairly simple, but if you want to justify a more rigorous way, then we do not have the tools to do that. Now, maybe there is an elementary proof of it, but if there is, it's probably very convoluted and very long. Okay, I want to show you another example. So this is an interesting example. So I found this example on a Harvard topology class a while ago. So I was looking for something to do with homotopic spaces, and they had that example. They had some kind of homework problem set. They had that example, and then I realized that example was actually taken from Moncrief's. So this appears in Moncrief's. So the example is, you're going to have two spaces. You're going to have X, and this is called the figure 8 space. figure 8 space. And it's called the figure 8 space because you basically have two circles that are connected at a single point. So maybe to help draw it, let's draw it like this. This is going to be our figure 8 space. And let's do this. Let's draw this. Let's draw this. And we're going to have a circle going like this. That it's supposed to be a perfect circle, but I'm not able to draw it. And then we're going to have another circle going like that. These pass through the center of the circles. And these circles have radius 1, of course, because why would you give them any other radius? This is the origin, horizontal, vertical axes. And then you're going to have, so this is why it's called the figure 8 space, figure 8 space. Now, the notation that we use for this is we write S1, I guess this is called like the 1-point union. You take two copies of S1. You see, this is a circle, two copies of S1, and you glue them at just a single point, 1-point union. So if you want to see the notation, but it's called the figure 8 space. We'll actually discuss this space later on and the fundamental group of it, but for now, for now we're not going to, we're not finding any fundamental groups now. We're just discussing homotopy equivalence. This is the figure 8 space. And then we'll have another space over here called Y. And this one is called the theta space, for reasons that you're about to see. So the theta space will look as follows. So let's just draw these axes to help sort of orient ourselves. And then we're going to draw the unit circle, of course. And then on top of that, we're going to connect this by a line. So we have a line that joins these 2 points. And that's why it's called the theta space, because it looks like a theta. So figure 8 space and the theta space. And it can be shown that these two spaces are homotopic, but they are not homeomorphic. Okay, so they're going to be homotopic, but they're not going to be homeomorphic. Now, this is the thing. In that Harvard exercise I came across, so if you want to find it, you can probably search Harvard topology homework homotopic space and look at maybe like the first results that come up, and then you'll see these kinds of pictures. So they provide a bit more detail if you want to look at this. So it can be shown these two spaces are homotopic. Now, do you want to do it intuitively or do you want to do it rigorously? So what we'll do now is, because I do not want to do this calculation, right? I'm going to be lazy. I do not want to do this calculation. I'm going to do it intuitively. I'm going to try to give you the intuition for why these two spaces are homotopic to each other, and also explain to you why they're not homeomorphic. And then, as a homework problem, you will have to actually find the functions that do it for you and show that those functions form a homotopy equivalence. So what's the intuition? So this is the way that I would see it. There's probably other ways you can look at this. Is I would look at this at that interval, and I would say, well, this interval, if you ignore the circle around it and you just look at that interval, well, this interval is contractible, right? We talked about contractible space. So it's contractible. So you can kind of take these 2 points and you can merge them together, and you can keep on pushing them together. And as these 2 points come closer and closer and closer together, when you push them together, as they come closer together, what's going to happen? This upper circle, these 2 points get identified together, so it goes like this. And then this bottom circle, well, this bottom semicircle, these two get glued together, so it kind of goes like that. And then this entire segment, it collapses down to a single point, and you have a figure 8 space. So that's like the intuition for why these two spaces are homotopic. There's a continuous way to change this into this. That's the idea here. Now, why they're not homeomorphic? So if you want, you can pause the video, maybe for like a minute or not, and see if you can come up with a very simple one-liner argument for why these two spaces are not homeomorphic. So the easiest way to see this is to focus on this origin. If you remove this origin from this space, the space collapses. Well, maybe I should not say collapses, because previously when I said collapses, I mean contracts to a point. But if you remove that point, you disconnect the space into two pieces. Now you have two components. The space becomes disconnected. Whereas this space, it does not matter which, like if you remove this one, it's still connected because it's connected over there. So it does not matter which point, where you remove a point, the space will always be connected. But this space is not, this space will no longer be connected after you remove away a single point. Okay, so that's why they're not homeomorphic. Now, what you need to do is you have to construct, to rigorously show that x is homotopic to y, we need to find two functions. One function maps x into y, and another function maps y into x, so that when you do f compose g, that would be homotopic to the identity on y. And when you do g composed f, that would be homotopic to the identity on x. So how does one find these functions? So let me describe these functions in words. So I'm going to describe these functions in words. And then your job would be to actually write down the formulas for these functions and then verify that these compositions are homotopic to the identity. So that means you will have to find the compositions, and then after you find the compositions, you then have to construct a homotopy that will do it for you. So here's the way this will go. You would take, you see this, so this is like the letter X. So you have three pieces here. You have this upper piece, middle piece, and lower piece. So the lower piece and the upper piece are easy to explain. You just take this semicircle and you bring it down one. So you can see if you bring it down one, you get this one. So if you have any point in this semicircle, you just slide it down and you end up somewhere over here. And with this lower semicircle, you slide it up. So you slide it up and you end up over there. So that is easy to understand. Now what do we do with this like letter X? We have this letter X, or I guess a chromosome. What do we do with the chromosome over here? So this one you just project down to the horizontal axis. You just project it down. So if you have, let's say, this point over here, you just project it down. You have this point over here, you just project it down. So that point down there, you project it down. So you can see when you project it down, you end up with this line segment from -1 to 1. So that's what you do with that, with the part in the middle. You just project it and you get this. So that explains this function. Okay, that explains that. Now, okay, so you have this function. So now you have to just find the actual equation for this function. So what do you do with the other one? How do you do this one? Well, this one is a little bit trickier. So the formula for this one's going to be trickier. But the way it works is, if you're going to be located, so if you're located anywhere on this line segment, it's going to be mapped to 0. It's going to be mapped to the origin. So this entire line segment gets mapped to the origin. So that one makes sense. That one's sort of easy to understand. But what if you're located in the upper hemisphere? So the idea is you have to find some kind of bijection between these two. That's the idea, right? You have to find a function that sort of opens up the semicircle. Well, it's, yeah. Oh, I'm sorry about that. It opens up, yeah. It opens up to this entire piece. That's what you need to find. So you're going to have to find a function that will map this piece to this piece bijectively, right? So you kind of imagine that, yeah, I mean, you just have to figure out how to do it in some kind of continuous way. So you have to write down the equation of a circle. So this is a circle that is centered at 0, 1, whose radius is 1. This is a circle who's centered at 0, -1 of radius 1. Then you have to solve. So there'll be some kind of radicals over there because, you know, equation of a circle has quadratics and stuff like that. So that's what the function is doing in words. And then after you do that, then you have to do compositions and construct homotopies with the identity. So that's what you got to do. So pretty convoluted, but I think it's a great exercise to learn what a homotopy is, homotopy equivalence. So this is example number 2. So this is the figure 8 space and the theta space, not homeomorphic. And also, in contrast with the previous example, neither any of these two spaces is a subspace of the other one. So this is example 2. For our third example, let us consider this. So X is going to be the punctured plane. Punctured plane. And Y is going to be the unit circle. I should not say the unit circle. Let's just say the one sphere, the one-dimensional sphere. We do not want to say unit circle. In topology, there's no such thing as a unit. So we have these two spaces, and we're going to, so if we look at the picture, so let's look at this picture. This is our punctured plane. We have a hole in the middle. And sitting inside the punctured plane is we have a sphere, a one-dimensional sphere. So we're going to draw the circle. So that's S1. Well, maybe I should draw it over here. So that's S1. So this is going to be X, and that's going to be Y. And we're going to claim that there's a homotopy equivalence between X and Y. So there's a homotopy equivalence between them. And I think this should be a good homework exercise to find that homotopy equivalence. So to find it rigorously. But what I want to just show you is I just want to show you the picture for what's going on. What you can do is you can draw, so you can draw a circle over here, right? So you can draw a circle inside the punctured plane. So you draw that circle. You sort of redraw that circle as sitting inside the punctured plane. And then from the origin, you can draw a ray going out to infinity. Right? You can draw a ray. And every single point on the ray will get mapped to where it is on that circle. So that's what you're doing. Right? It gets mapped to where it is on the circle. And right, so you have this. And maybe the intuition here, maybe you will find this helpful, but to kind of maybe redraw the picture. So there's your hole. So this is the stuff on the outside. And then this is the stuff on the inside. So whatever you have on the inside, you can sort of deform it, right? You can take all of this space and you can just pull it back until you get to the circle, right? You start with that hole and you just keep on pulling it back, like continuously. You see, you can continuously pull it back. It's important that you have a hole, because if you did not have a hole, then you would be rupturing your space, right? You would have to rupture the space in order to pull it back. But because you already have a hole in your space, you do not have to rupture anything. You do not have to destroy your space. From that point, you just pull all of that stuff in the space through the space until it lands on the circle. And then everything that is outside the circle, you just can bring it back in, right? You have all that space there to move through, and so you can continuously move everything, right? So you can continuously move everything to this boundary circle, right? You can just continuously move everything here. And so the idea is that because of these two are therefore homotopic to each other. They're homotopic. So it's kind of the idea, and these pictures give you a sense of how to construct the homotopy equivalence. So you can think of that. I think that would be a good homework problem for you to think about how to construct that homotopy equivalence that will do it for you. Now, these spaces are not homeomorphic. And I would suggest, if you want to challenge yourself to see how far well you understand the material, you can again pause this video for a moment and try to think of a reason for why these two spaces are not homeomorphic. Like, what is the reason here for why they're not homeomorphic? So the simplest reason you can give, you should of course notice that both of these spaces are connected. And there's different arguments you can give. You can use some kind of connectivity argument that we did before, because if you remove 2 points on a sphere, then the sphere will become disconnected, whereas you can remove an infinite number of points in the punctured plane and it still stays connected. But perhaps even easier, an even easier type of explanation would be that the sphere, this is a compact space, and this is not a compact space, right? It's unbounded. This is like the plane, it's unbounded. Heine-Borel, it's also not an open subset of the plane. So, I'm sorry, it's also not a closed subset of the plane. So Heine-Borel will tell you it's not compact. It violates both requirements. Okay, so that's like one way to see it. And that brings us to our main theorem. So this is like the main theorem that we want to do. Main theorem. So it says that suppose f from x to y, maybe just to even indicate, let's say x comma p to y comma q. So this just indicates that this is a continuous function. It maps p to q because the fundamental group is always taking place at some point. At some point is a continuous map. Is a continuous map. And f is a homotopy equivalence between x and y. So then f star, this is the induced map. So anytime you have a continuous map, that continuous map induces a homomorphism of groups between the fundamental groups. Then the induced homomorphism coming from f is an isomorphism. And so x and y have the same fundamental group. That's really like the main theorem. So this is what we want to prove, that if we have a homotopy equivalence, then that homotopy equivalence will give us an isomorphism between the fundamental groups. Now, to prove this theorem, we're going to need a lemma. And I'm not going to prove the lemma. What I will do, I'm going to be lazy, and I will just direct you to Moncrief. So Moncrief proves this lemma. So it'll be a homework exercise to read through the lemma and make sure you understand it. And here's what the lemma says. We'll draw some, we'll give an explanation for what the lemma says, and then it'll be used in our proof. So there's going to be a lemma here. So this is the lemma. It says, okay, so here's what it says. So say f maps x comma p to y comma q. That's a continuous map. And we have another map. Now, the reason why another map gets introduced is because whenever we say that something is a homotopy equivalence, that means it has a homotopy inverse. There's another map G going the other way around that will play the role of a homotopy inverse. So let's say there's a G. Now this G, in this case, it's not going to be the homotopy inverse, but they're going to both be homotopic. So this is going to be x comma p. But when you have another function, it does not have to map that point to q. It can map it somewhere else. It can be mapped somewhere else. So G is going to map this somewhere else. Let's call it y comma r. Okay, so say we have this, We have this. So if we look at the fundamental groups, we go from X comma P, and then F star. That's the induced map that gives us a mapping between these two fundamental groups. But we also have G star, which is going to be a homomorphism between this fundamental group. So in this case, the same fundamental group. To pi 1 YR. Okay? And we want to describe the relationship between F star and G star, because they are moving the points around. So we want to describe the relationship between them. Now, you probably recall, so I guess we have to recall something. Yeah, I guess we have to recall something. We've talked about this before, but let's just recall this. So say we have a path, and I need to make up some notation for a path. Let's call it phi. Say phi is a path from P to Q in space X. So we construct the following map. I called it mu. I think Moncrief calls it by some other notation. So we called it mu for map. That takes you from this fundamental group, so the fundamental group of X at P, and it sends you to the fundamental group of X at Q. And this mapping here, if you recall how it goes, is that if you take a homotopy class at P, so the homotopy class, let's call it theta, it gets mapped to, you do phi reverse, juxtapose theta, juxtapose phi. Okay, and this mapping is an isomorphism. So we talked about this before. You also had something about that on your homework. So this is what happens when you change the base point in the fundamental group. So you have like two different fundamental, well, they're not really different, they're isomorphic, but you have two fundamental groups at different points, and there's an isomorphism between them, which is described by this mapping. So you take a homotopy class at P, so you go in the reverse. So theta, so phi goes from P to Q, so theta reverse goes from Q to P. So this goes from Q to P, then theta, it's a loop at P, so it goes from P to P, and then theta takes you from P to Q. So the entire path goes from Q to Q. So this is some path that begins, a closed path that begins and ends at Q. So this is now a loop that is located at Q. So this is the isomorphism. So what Moncrief says, the lemma that he uses, is he says that there is one of these isomorphisms here that will make the diagram commute. And the way you get this isomorphism, this mapping, comes from the homotopy. Oh, so I forgot to say something. So at the moment we have F and G, these are mappings, so we have this. And suppose F is homotopic with G. So there's a homotopy H from X cross I into Y, where Hx of 0 is equal to f of x, and Hx of 1 is equal to g of x. Okay. Now, this homotopy gives a path in Y as follows. If you look at this homotopy, and for x you set it equal to p, so you set it equal to p because we start at p, so we're going to set it equal to p, pt. gives a path. So this is now a function from I into Y. You see, what you're doing is H is a function of sort of like two variables, the X variable and the time variable. So you're fixing X to be P. You're fixing X to be the point. You're fixing X to be this point right over here. And then you're letting time vary from 0 to 1. And what is this? This is by definition a path. This is a path in Y because it lands in Y. When time is equal to 0, what is this? This is precisely f of P, which in this case is Q, and its H of P1 would be G of P. That's the other one because it's a homotopy. When time is 0, you get f of X, and when time is 1, you get G of X. So this would be G of P, but G of P, by assumption, that's equal to point R. So that is equal to point R. So the homotopy gives you a path. You use the homotopy to create a path. So homotopy creates a path for you in this way. So let's call that path, let's call this path phi, right? So this entire thing is phi of t. That's your path. The point is being fixed throughout this, so this is just a function of time, phi of t. And the lemma says that it turns out that this is there's an isomorphism here, and this isomorphism is precisely mu of phi. So if phi is the path, you see, phi is the path from Q to R. Phi is the path from Q to R. So you're using the homotopy to create a path. You're not just picking a random path. You have to be very careful what the lemma says. You're not just saying, oh, I'm going to just pick up a random path, I'm going to put it in there. Recall what we said. You get different mappings depending on what paths you pick. If you pick a different mapping from Q to R, this might be a totally different mapping, and this relationship might not hold. But you're using the homotopy to create the mapping. So by assumption, if you assume that F and G are homotopic, then there's this homotopy. And then you can use that homotopy to create the mapping. Homotopy, it's a mapping from X cross I. So at X, you're going to, instead of varying X, you're going to set it equal to that point P in the beginning, and then you let time vary from 0 to 1. And therefore, you're creating a path in Y that begins at Q and it goes to R. So you've just created a path here, and this is an isomorphism. So this is like the notation for an isomorphism. So this is like overloading. We use this notation quite a lot. We use it for homeomorphism, isomorphism, homotopy. It's just like the context. It's supposed to resemble that two things are almost the same, right? That's what it's supposed to mean. So this is an isomorphism between the two, and this diagram commutes this relationship. So that would mean that if you do F star follow this, that will give you that. So that relationship is satisfied. So that's what you have to prove. It will turn out that if you do G star apply to a homotopy class, and you just let G act on that, you might get something that is different from this, but on the level of homotopy classes, they're going to be the same. And that's kind of the whole proof of the lemma, is to justify that relationship, because we're going to be using that relationship while we do this proof. So this is the main theorem, and when we give the proof of the main theorem, you're going to be using this lemma. So if you have Moncrief, you can open up and see what he does. He uses some other notation. I'm not a fan of his notation. I find it confusing, but that's what he says. And you can look at his proof and try to figure out. So this is the lemma that we're going to be using. And now we can start talking about how you prove this. Let's maybe get rid of all of this. So you probably noticed that the class now feels very different from what we were doing before. So perhaps you like it more. I'm not sure. I think this stuff is more interesting than what we've been doing before, especially the stuff with functors that was fairly abstract and quite interesting, and the proofs were quite nice. So now it feels very different, right? It's no longer point set topology where you have subsets and elements and unions, intersections, or anything like that. Now it's very different. So how do we prove this? So proof. So let's begin with this. So let G be a homotopic inverse for F. Okay, so that would mean that if you do F compose G, that's going to give you the identity on Y. And if you do G composed F, that will be homotopic to the identity on X. The reason why you know that this exists is the assumption that you have a homotopy equivalence. Homotopy equivalence basically means you have a homotopic inverse. So it's almost an inverse, but it's not really an inverse. It's homotopic to the inverse. So let G be the homotopic inverse. And now let's construct the following. So we have pi 1 x comma p, and that gets mapped to pi 1 x comma q. So f is a mapping from this to this, and so it induces a mapping from this group to that group, homomorphism. And I'm going to call that homomorphism f subscript p star instead of just f. You're going to see the reason why I have to decorate them, because I'm going to have another fundamental group at a different point. So technically you have different mappings, and to avoid confusion, you put some decorations on them. And then you have a mapping from the fundamental group of xq. But when you use G, let's say that G of Q is equal to R. So G, I guess I should have said it over here. G is the homotopic inverse. It goes from Y to X. So what we're saying here is P is being mapped to Q, and then G takes that point Q and it maps it to another point in X. Let's call it R. Or maybe it will be better to call it P prime, so that we know P is coming from X. Yeah, so that we know that this one's coming from, that this one is coming from P prime is an X and not an Y. Okay, so this one we're going to call, this is pi, oh, small mistake. I wrote an X over here. I, of course, meant Y. And this is going to be G star pi 1 Y comma, I'm sorry, X comma P prime, like this. And this one I'm going to call G prime. I'm sorry, I'm just going to call this G star. I'm not going to put a decoration on it. I'm not going to write G subscript Q star, because I'm only going to have one G. There's only going to be one G, as opposed to we're going to have two different Fs. So we sort of have to distinguish them. We have to be a little bit more careful with them. And this one, and then we're going to map this again, because so we have F. So we're basically doing F composed G and G composed F. So here we have, so we have F going first, G going first, and now we're going to use F. So we can also map this to pi 1 of Y comma Q prime. So we're going to assume that F P prime is equal to Q prime. So let's assume that. So F maps P prime to Q prime, and then this mapping, this is F, but it's mapping P prime to Q prime. So this is going to be F P prime star. So this is the picture that we have involving these maps. Now we have to use the fact that we have a homotopy equivalence, right? That we have a homotopy equivalence going on over here. Now, the homotopy equivalence that we're going to use is, we know that when you do G composed F, that this is homotopic to the identity on X. Okay, we know this. So what does that mean? We have, so the identity on X is a map from X to X, and G composed F, it's a map. So actually, let's say it like this. It's a map from X comma P to where? So let's see where that goes. X comma P. So the F here, it's sending f sends p to q, and g sends q to p prime. So this is from x comma p prime. Okay, we have this. Whereas the identity mapping on x, to be more specific with the points, this is sending x comma p to x comma p. So that would mean that when we pass to the fundamental group, we have the following relationship. So the identity on x, it induces a map from pi 1 x comma p. Perhaps it would be better. Yeah, perhaps it would be better to write it like this. So let me write it as pi 1 x comma p. The identity on x, it induces an identity mapping, and that would be pi 1 x comma p. Okay, we have this. And this one, this composition, it induces a mapping of these fundamental groups. So this is G compose F. This induces a mapping pi 1x comma p prime. Now, this is where the lemma is going to come in. Notice that this composition is homotopic with the identity. And by the lemma, so I took down the lemma, but by the lemma, it will tell you that there is a path from P to P prime coming from the homotopy. So there's a mapping coming from the homotopy. You do not even have to write out what the mapping is. So that's like the one part where this proof is a little bit simpler. You do not even have to write out what the mapping is. You just need to know that it exists. So there is a mapping coming from the homotopy. Let's call this mu subscript phi. Right? So there's some mapping from P to P prime, which this, so you have a homotopy between this one and this one. The homotopy is going to create a mapping from P to P prime. It's a path from P to P prime, so some path in X. And whatever that is, now you have this kind of relationship, that this kind of now diagram will commute. And, right, so you have this. So now you can, so this is an isomorphism, right? This thing is an isomorphism. So if you wanted to, you can make the arrow go backwards. You can make this, you can make this arrow go backwards. So you can make this arrow go like this, and then you just use the reverse path, right? The reverse path. And the induced map of the identity is the identity, right? That's the property of a functor, that it preserves the identity. So this is just the identity. So because it's the identity, you can just, I mean, there's nothing wrong. You can just make it go the other way. You can just make it go like this. So what does this show us? So this shows that when you do G compose F comma star, that is equal to, so this diagram commutes. So this one, it's this followed by that. Mu phi composed with, well, you would say composed with the identity, but there's no reason for you to even use the identity anyway. It's just this, right? This is an isomorphism, right? This is an isomorphism. Now we use the property of the fundamental group, the property of the functor of the fundamental group, that the induced map of a composition is the composition of these two. So G, this would be G star composed with F star. But here you have to be careful, which F star is this? Which one is this? So be a little bit careful here which one we're referring to. Which one are we referring to? So you see, this is the F in the beginning, followed by G. So this is the one that maps P to Q. We have G mapping Q to P prime. So this is the F that we had in the beginning. So this is FP star. So this is really F P star. Right? We kind of open up what that is, and we just understand that that was the first f that we were using. So this is equal to mu phi, right? So basically, the fact that it's equal to this does not matter. So this is an isomorphism. Is an isomorphism. And a similar argument will show, and now you do it the other way around. It will show that G star composed, but this time composed with, on the other side, Fp prime star is an isomorphism. Okay? So this one is an isomorphism, and this one is an isomorphism. So if we return back to this picture, we're saying that if you do this composition, you get an isomorphism. You get a mapping from here. So the composition will give you a mapping from this one to this one. That's an isomorphism. And if you do this composition with these two, that will give you an isomorphism between those two. So what does this mean? So from here, it follows that G star is therefore a bijection. And so G star is an isomorphism. Because we already know it's a homomorphism because it's always a homomorphism. You just have to show it's a bijection. So this is just, I mean, you're basically using the following fact. I mean, you're basically saying this. Let's say you have a mapping from A to B, and then you have another mapping from B to A. And it turns out that if you do G composed F, so usually we say the identity, right? This is usually the way we say it. We say the identity on A. But let's say instead of being an identity on A, this is a bijection. So this is a map from A to A, and you know it's a bijection. So instead of an identity, it's a bijection. And if you do it like this, now it's a mapping from B to B, and it's a bijection. So then F and G are bijections also. Okay, they're bijections also. So that's basically what's going on. The one difference is that you have two different mappings here, and you have a G, but you have the same G. That's the thing. The G is the same here, but these are the two different mappings. So you ignore the F, you just focus on the G. So G star is therefore a bijection. So we have shown. So if you're being very careful, you will notice we did not prove that F star is a bijection. We did not prove that F star is the isomorphism. We proved that G star is the isomorphism. But of course, if F is homotopic, right? If F is a homotopy equivalence between X and Y, then G is a homotopy equivalence between Y and X, right? That's the homotopic inverse. And then you can repeat the whole argument with Y and X interchanged and do everything that we just did. And so in the end, you end up getting that F star would therefore be an isomorphism between these two fundamental groups. So this is it's not an easy proof. And the complications here is because these base points are moving around. And you have to use that lemma in there as well. So this is definitely not an easy proof. But now that we know it, we'll be able to take the advantage of it when we need to. And so this concludes this lecture. And next lecture, we're going to start discussing how you justify that the fundamental group of the punctured plane is isomorphic to the group of integers, and that would lead to some interesting consequences that we will see.